You're driving down the highway and you see this dashboard view, the sudden glow of the check engine light. Do you pull over right now or keep driving to the shop? This engine diagram outlines the answer. A solid yellow light means a fault affecting emissions. It's safe to drive, but you'll burn extra fuel. A blinking red light indicates a severe misfire. You must stop immediately to prevent exhaust damage. We look at this top-down engine blueprint. The engine operates as a continuous, closed-loop system. The central ECU reads data from the intake's mass airflow sensor, measures resulting combustion through the exhaust's O2 sensor, and manages vapor via EVAP and EGR pathways. When that warning light comes on, it means one specific part of this loop has failed. We don't have to guess what broke. We just extract the exact data the engine is already trying to give us. We extract that data using a strict three-step protocol, shown here on this scanner interface. First, we pull the diagnostic trouble code, or DTC, to identify the affected system. Next, we analyze the freeze frame data to see exactly how fast the engine was running and how hot it was the second the light triggered. Finally, we monitor live data curves to verify if a sensor is actually dead in real time. Let's look at how these failures actually happen, starting with the intake. This macro view shows the delicate hot wire inside a mass airflow sensor. If you use a cheap or damaged air filter, microscopic dust particles and oil vapor slip past and coat this wire, physically insulating it from the incoming air. Because it's insulated, the sensor cools down slower. It reports to the ECU that less air is entering the engine than there actually is. The ECU responds by injecting less fuel, which actively ruins the engine's combustion ratio and triggers a warning code. A similar physical blockage happens at the other end of the cycle. If we look inside the exhaust, we see the O2 sensor. Heavy carbon buildup from incomplete combustion or impurities in cheap fuel can cake onto the sensor's tip. This makes its readings sluggish or stops them entirely, breaking the computer's ability to correct the air-fuel mixture. If you plug in a scanner and just hit clear code without removing the carbon on the O2 sensor or the dust on the MAF wire, the computer will detect the exact same incorrect voltage on the next drive. The light will come right back on. Ignoring these early warnings creates a precise chain reaction. This image of a glowing catalytic converter shows the result. It starts upstream with something as simple as a dead spark plug causing an engine misfire. That misfire means the cylinder fails to ignite its mixture, pushing a cloud of incomplete combustion directly into the exhaust pipe. That unburnt fuel hits the extremely hot, honeycombed precious metals inside the catalytic converter and ignites. This raw fuel fire permanently melts the internal structure, triggering a P0420 code. What started as a cheap spark plug replacement is now a repair bill costing thousands of dollars. Engaging. Let's test your understanding of the systems we mapped earlier. Look at the left side of the split view. A driver finishes refueling but forgets to twist the gas cap until it clicks. Based on our closed-loop model, which system detects this? What type of code triggers? And how severe is the threat? We can check our answer against this threat matrix table. A loose cap breaks the vacuum seal in the fuel tank. The EVAP system detects the loss of pressure and throws a P0442 or P0455 vapor leak code. As the matrix shows, this is a minor pollution issue with a very low threat to the engine itself. Knowing how to classify that specific threat level prevents a mechanic from overreacting to a loose piece of plastic, while ensuring they catch a severe misfire before it cascades. Once you have a code, you have to verify the hardware. This engine bay map highlights the physical targets. You start with target alpha, checking the gas cap. Then target beta, inspecting the air filter box and MAF connector. Finally, target gamma, physically running your hands along the lines to find cracked vacuum hoses or wires chewed by rodents. If a component just needs cleaning, we use light intervention. On the left side of this comparison panel, we see a MAF sensor being sprayed. You must use a dedicated, residue-free MAF sensor cleaner. If you spray harsh chemicals like carburetor or brake cleaner onto that delicate hot wire, the solvents will instantly destroy it. Heavy intervention is required for permanent hardware death. Look at the right side of the panel. If an O2 sensor's internal heater circuit burns out, no amount of chemical cleaning will bridge that broken electrical connection. It has to be completely unthreaded and replaced with an original equipment manufacturer part. With the new part installed, you clear the digital code with the scanner. But the job isn't done. As shown in this highway driving view, you must complete a drive cycle. By driving at specific speeds and varying your RPMs, you force the ECU to run a fresh self-test on the emission system and verify the repair. This assistant view summarizes our end goal, treating the vehicle as a protected, logical system. The scanner tells you what failed, but strict, routine maintenance, like tightening the gas cap, changing the air filter on schedule, and replacing spark plugs before they misfire, is how you keep the check engine light off in the first place.